All right, in this video, we are going to talk about regression models, which is basically just writing an equation for a set of data. And so we're going to start with a warm-up to review arithmetic and geometric sequences because that's going to help us identify what model we want to use. And so looking at this first example, I see that this sequence is going from 6 to 10, which is adding 4, 10 to 14, adding 4, 14 to 18, adding 4. And so this would be an arithmetic sequence because we are adding. So we call that a common difference. And that common difference is 4. And so in recursive form, that says we can get to any term by taking the previous term and adding 4. Now that's just telling us what the pattern is. This isn't a helpful formula. A helpful formula would be the explicit form, which says you start at the first term, which in this case is 6, and you add the common difference 4 or n minus 1 more times. And so if you were to look for the 10th term, you'd start at 6 and you would add 4 9 more times to get to the 10th spot because we're starting in the first and we have to go 9 more spots. Okay, something I want to point out about arithmetic sequences is they are linear. Okay, and so if I wanted to simplify this explicit form, I could distribute the 4 and then combine my 6 and negative 4 to be 2. And so 4n minus 2 would be another explicit form that we could write. Okay, and so this is a linear relationship. You can see that your slope is 4 and your y-intercept is negative 2 if I were to graph this. So the y-intercept kind of, not negative 2, positive 2. 6 minus 4 is positive 2. And so another way you could find that y-intercept is it corresponds to the 0th term. So if I were to go backwards, here's a 1. If I were to go backwards, I would get to 2 because 2 plus 4 would have given me the 6. And so the 0th term corresponds to the y-intercept. And your common difference corresponds to the slope. Okay, looking at this next sequence, we are multiplying by 3, which means this is a geometric sequence, which means we have a common ratio, which in this case is 3. So in recursive form, you get to any term by multiplying 3 by the previous term. And for the explicit form, we get to any term by taking the first term and multiplying it by the common ratio n minus 1 more times. Okay, and so what I'm hoping you have noticed is that geometric corresponds to exponential functions because we are multiplying. And so another explicit form would be our a times b to the x, which means we need the y-intercept, which means we would just go backwards to the 0th term, and 2/3 times 3 would give us the 2. And so we would have a 2/3 times 3 to the n as an equivalent form. Okay, and so what we're going to do in this lesson is we're actually going to use our calculator to get these equations, the ones I've highlighted, because our calculator always puts it in linear or exponential form. They don't put it in terms of n minus 1. And so half the battle is just identifying whether you have a linear function or an exponential function, and we'll also talk about quadratic functions. Okay, and so something that's important to note is that regression models only work with adding and multiplying. Okay, and so with this, we can remember that subtracting is adding a negative number. And dividing is multiplying and dividing is multiplying by a fraction. So for example, multiplying by 2 or is multiplying by 1/2 is the same as dividing by 2. Okay, and so now we're going to talk about how to identify if you are dealing with a linear, exponential, or quadratic. Linear and exponential we just talked about. Okay, it corresponds to arithmetic. And so one thing you want to note is that the pattern for x is always adding 1. Otherwise, you're not going to be able to identify any pattern. So make sure you are always adding 1 to your x's, and then it would make sense to look for a pattern in the y's. And so if you are also adding any number, you're dealing with an arithmetic sequence, which corresponds to linear function. If you are multiplying by a number, you are dealing with an exponential function because that corresponds to a geometric sequence. Okay, so adding is linear, multiplying is exponential, and then for a quadratic function, you actually look at your second differences, and so we'll talk about what that means. Second difference is constant. And then that would be quadratic. Okay, and so you can use a TI-84 or TI-83 using linreg, xreg, or quadreg, but Desmos is actually a way easier to do that to get all of these equations. Okay, so if you are dealing with a linear, you want ax plus b or mx plus b. If you are dealing with exponential, you want a times b to the x. And if you're dealing with a quadratic, you want ax squared plus bx plus c. Okay, and so here are the listed steps for using a calculator, but we are going to use Desmos. And so you can kind of ignore these if you're following along with these notes. All right, so the first thing you have to do is identify what kind of function you are working with. And so looking at number 1, I can see that my x's are going up by 1s each time, which means it makes sense to look for a pattern in the y's. And so the y's, you'll notice, are also going up by 1. And so that means this is a linear function. We're adding, so it's arithmetic, which means linear function. And so for linear functions, we're looking for mx plus b. And honestly, you can already see that the slope, m, is 1. And you can see the y-intercept, b, is 4. And so without running a regression in the calculator, because this is perfectly linear, you could go ahead and write your equation 1x plus 4. But if you need to use regression, and you're going to do this for all of the examples, is you can choose star. Click this plus sign, click the table, and then you are adding your x's to the x column. So -2, -1, 0, 1, 2, 2, 3, 4, 5, 6. Now, if you look over in the blue on the left, right next to where it says 1, click that line with the dots, and it automatically puts your linear regression equation. And so it says 1x plus 4. It defaults to linear, so if you're not working with a linear function, you're just going to click that down arrow and choose which one you want. We are just going to be working with quadratic and exponential, and so those are the ones we're going to choose from. Okay, and so for number 2, we see that the x's are going up by 1 each time, and then the y's are multiplying by 3. And so that means we are working with an exponential function. which means we are looking for a times b to the x, where b is that multiplier. So we can already see, since this is perfectly exponential, we can see that b is 3. And then a is our y-intercept. And so we can see a is 9. And so without running a regression, we could go ahead and write y equals 9 times 3 to the x. But to use the regression, you would click your plus sign, add your table, type your x's, type your y's, and then that line with the dots right next to the 1 gives me a linear regression equation, but we know it's exponential, so we are going to choose exponential, and that's where we see 9 times 3 to the x. Okay, looking at this next one, I see that the x's are going up by 1, and so it makes sense to look for a pattern in the y's. And I know right off the bat that we're not multiplying each time, because once we get to 0, it would stay 0 the whole time. And so I'm going to go ahead and look for an adding pattern. So to get from -6 to 0, we add 6. To get from 0 to 8, we've added 8. To get from 8 to 18, we've added 10. To get from 18 to 30, we've added 12. Okay, and so obviously that is not constant, but if you look at the differences of these red numbers, the differences of the differences, that's called the second difference. And so here you can see from 6 to 8, we've added 2. From 8 to 10, we've added 2. From 10 to 12, we've added 2. Okay, so the numbers in red are your first differences. The numbers in blue are your second differences. Okay, here my second difference is constant. And so that means we are working with a quadratic function. And there is not an easy, quick way to write the equation for a quadratic. So this is where the regression is very, very helpful. So clearing out what is already in my calculator, we are going to add this new table. Then click the line, and it automatically does linear. So remember, you don't want to choose linear if you know it's quadratic. So go to quadratic, and here we can see our equation y equals 1x squared plus 5x minus 6. So for quadratic equations, we're looking for ax squared plus bx plus c. And that's what our calculator just gave us. They may leave the 1 invisible, and so if you don't write the 1, you would still be correct. Okay, and so let's look at number 5, where they're just giving us ordered pairs. If they're giving you ordered pairs, still turn it into a table just so you can start identifying the pattern easier and also use your regression easier. Okay, so I've got the 0.08, I've got the 0.13, I've got the 0.2, -4, 3, -13, 4, -24, and 5, -37. Okay, and so looking at our pattern, our x's are still going up by 1. And then looking at our y's, it goes from positive and then remains negative for the rest of the time. And so we know it's not multiplying. So now we're looking at an adding pattern. So from 8 to 3, it's subtracting 5. From 3 to -4, it's subtracting 7. From -4 to -13, it's subtracting 9. From -13 to -24, it's -11. And from -24 to -37, it's -13. So those are not constant, so this is not linear. But from -5 to -7, that is subtracting 2. And then from -7 to -9, subtracting 2. To get to -11, subtracting 2, subtracting 2. And so here our second difference is constant. So I'm just going to write second difference, which means we are working with a quadratic function again. Okay, and so we are looking for ax squared plus bx plus c. And this is where the regression is very, very helpful. Okay, so now adding my table. And then right in the blue to the left of the table at the top is that line with dots on each side. Click that, choose quadratic, and we see our equation is -1x squared minus 4x plus 8. And you can also see it graphs it perfectly through the points on my graph. Okay, and so once again, that will probably leave the 1 invisible and just write -x squared. But either one would be correct. Okay, for the last example, we're going to look at a word problem. And it says the table shows the number of new branches in each figure of the pattern. What is the pattern you can use to complete the table? Represent the relationship using words and an equation. So we're going to just do what we've been doing. And so looking at our first term, there's 3 branches. On our second, there is 1, 2, 3, 4, 5, 6, 7, 8, 9. And then looking at our last one, we could count, there's 27. And so each time we're increasing our x's by 1. And we are multiplying the y's by 3. Okay, and so that means we are working with an exponential function, which corresponds to a geometric sequence. And so we're looking for a times b to the x. And so this is another one where we don't actually have to do the regression because it is perfectly exponential. We see that our b value is 3. And to get our a value, we just need to add our y-intercept, which means we need to divide by 3 to go backwards, and that would give us 1 for our a value. Okay, and so our equation could be 1 times 3 to the x, which is what Desmos would give you. And then just like the other examples, they may leave that 1 invisible and just write 3 to the x, and you don't even need the parentheses.